Hi, everyone. Thank you so much for joining us here today for our Carson Water Subconservancy District Alluvial Fan Mapping Study. This was a really great project, and we enjoyed working with all the Nevada partners that were on this project with us, and we listed them there at the bottom of the slide. So for today's presentation, we'll be giving you an overview of what the study entailed and then our findings. But before we go ahead and jump into that, we'll do a few quick introductions. And so I'll go ahead and kick us off. My name is Elise Jarrett, and I'm a water resources planner with the Army Corps of Engineers, and I'm out of the Sacramento district. And today I have John Newton joining me here. So I'll pass it over to John for a quick introduction.
Hi, this is John Newton. I'm a hydraulic engineer at the Walwala District of the U.S. Army Corps of Engineers.
All right, great. Thanks, John. And before we jump into the presentation, I would like to also introduce another key Corps member, Lou Hunter, who wasn't able to attend the presentation today, but he was our senior geologist on the study, and he was the one who did all the geologic analysis. And so I'll be covering the information that he put together and provide you guys with that overview. So for our presentation outline, I'll be providing a study history and touch base on the phase 1 and phase 2. And then I'll be covering the geologic assessment. And then I'll pass it over to John, who will talk with you all on the hydraulic assessment piece. And then we'll wrap it up with looking at what are the next steps. So for the study history, the way it worked out, broke out into a phase 1 and a phase 2. And so for phase 1, that was completed back in 2017, and that entailed looking at or mapping and classifying 297 alluvial fans based on their apparent risk that fell within the Carson River Watershed. And so the figure here is showing all of the fans that were mapped. And then this rolled into our phase 2 efforts, which we completed in 2020, so just last year. And this effort included identifying a subset of those previously identified 297 fans. And that subset underwent further geologic and hydraulic analysis. And so I have a clearer picture on the next slide, but you can see here kind of the call outs on where those are located. And so for the phase 1 results, this is just a summary slide on the distribution of the risk ranking. And this table here does a really great job capturing the information. And so out of the 297 fans, there were 202 fans that fell within the moderate risk ranking category. And then there were 77 fans that fell within the high risk ranking category, and then 18 fans that fell within the low risk. There were no fans that fell within the very high or very low risk categories. And then the town of Dayton, Carson River Watershed, that was the area that had the most high risk fans, which came out to be 20 high risk fans in that area. And so for the goals of phase 2, so once we delineated those 297 fans, so for the goals for phase 2 is that we wanted to develop additional in-depth data sets for planners and city and or county managers to increase their knowledge of alluvial fan risk. Another goal was to increase the certainty of alluvial fan delineations on those selected fans. And then lastly, to conduct hydraulic analysis on the selected fans. And so the main significance or the biggest significance of this second phase of this project was to get a better understanding and prioritize the watershed risk, which could help prevent further development in high hazard areas, and also develop strategies to mitigate in areas where development may already be occurring. And so this was the map that I was referencing a little bit earlier. And so for the geologic assessment, that the main goal was to look at the geomorphology to evaluate and identify geohazards. And this is specifically looking at areas that are susceptible to floods and debris flows. And so for the methodology, out of that 297 out of the 297 fans that were originally delineated, we looked at 8 fans. And so there were 6 fans that were located in Douglas County, and then there were 2 fans that were located in Carson City County. And so here on the map, you can see that we have 2 fans that are located down by Genoa. There were 4 fans just east of Indian Hills, and then 2 fans were located just northeast of Prison Hills. And in order to perform the analysis that this phase 2 would cover, there had to be LiDAR data available. And so we initially were working to also include Lyons County in our analysis, but due to LiDAR limitations, we unfortunately weren't able to include those fans at this time. So for the geologic assessment, so Lou used only the bare earth data from the LiDAR collection. He used the digital elevation models and then generated contours. So he did a 1 meter, 2 meter, and 5 meter contour. And then he used slope maps, so looking at the surface morphology, calculating the gradients, and then that ultimately played into defining the outer toe of the fans. And so down in these 2 bottom examples, it's maybe a little bit hard to see. They're outlined in red, but we can see the outline of the fan boundaries. And then from there, Lou used the LiDAR hillshade and he superimposed those contours. And then he used slope maps and aerial photography to get a better feel for what was going on out there. And so he initially did a lot of in-office work, first developing these maps, running these different models to get those boundaries. And then he performed several site visits to have boots on the ground to actually fact check and to verify the outputs that he was able to develop in the office. And so this top right photo here was using some aerial. And so one thing that Lou was looking at was different colorations in the picture here. And so you can see right where the arrow is pointing, it's a little bit lighter. And so that was one indication to Lou that there may have been a recent deposition that occurred in the area. And so then when he went out into the site visits, he was able to verify that. And so that bottom left photo is showing that, he was looking at that fan. It was fan 78. And he noticed that there was a sandy alluvial deposit that had occurred there. And so then after Lou did the initial kind of computer work, he went out and fact checked with boots on the ground work. He was then able to identify and evaluate the geohazards that were present in each of those fans. And so this is a summary of Lou's analysis. And so he determined that all fans, we're looking at 8 fans. He determined that all 8 fans were active, but at varying degrees. And so fans 79 and 82 were determined to be pretty benign, but fans 44 and 45 were determined to be very active. For the alluvial transport and deposition occurring, that channel and sheet flow deposits were common. And then he also noticed that there were fresh deposits along the road during his site visit. And then for debris flow possibility, so sites or fans number 44 and 45 were most susceptible to debris flows. And then also for fans 81 and 116, there were steep sections near the fan apex that could contribute to potential debris flows, and then also potentially fan 78. And so with that, I will pass it over to John, who will share with you all the hydraulic assessment.
Okay, so the purpose of the hydraulic assessment was to determine what area might get inundated during a 1 in 100 probability event. And to do this, we first needed flow, but none of these sites actually had gauge data, so there's no historic flow record. But we did have precipitation data. So we used the NRCS's WinTR55 program to generate hydrographs for each of the watersheds. In the example on the slide here, there are the hydrographs at the left correspond to the 4 watersheds at the right. And these hydrographs were fed in at the apex of the alluvial fans. Now, in addition to this main flow from the watershed, we also had other flow that came into the system, which is indicated by the blue areas. And in those areas, there were several small tributaries and some overland flow that came directly into the area of interest, which is the pink area. So for the blue areas, what we did is we actually created an HEC-RAS two-dimensional model and applied rainfall directly to the model. And then that flowed into this pink area, which is the area of interest. The pink area became a more detailed HEC-RAS two-dimensional hydraulic model that helped to define the inundated area. Next slide. So what you see coming in here is the actual output from the two-dimensional HEC-RAS model. And this is the inundated area. The depth shading is based on how deep the flow is. And there are some areas on here that are shaded in kind of a lighter pink color. These are the areas from the geological assessment that were determined to be active for these particular alluvial fans. And we'll get into discussing those a little bit more and the implications for that. But for a moment, let's continue on here and talk a little bit about the HEC-RAS model. Next slide. So this slide shows an example of one of the alluvial fans that we model. In this particular case, we actually applied rainfall in the HEC-RAS model directly on top of the alluvial fan, in addition to the hydrograph inflow, which you can see at the bottom left of the screen here. And in a moment, we're going to play a video here that'll show the actual simulation, and you'll see the flow come down that channel and under a culvert and then gradually begin to inundate the area. What you see now is actually the maximum inundated area. So let's go ahead and play that video. So you can see the flow coming in and under the culvert. The hydrograph in the upper right there is what's being fed in. And as we get to that peak, you'll see more and more area become quickly inundated. So now what's happening here, it's showing what would happen if there was no movement, if there was no erosion and deposition and no channel movement, what area would actually become inundated. And in reality, in this particular alluvial fan, there could be some potential movement. And so to account for this potential movement, we had to use another method to assess this. This particular version of HEC-RAS did not have the capability to handle sediment. And as a result, we used the FEMA fan program, which is discussed in the next slide here. And the fan program gets us this movement. It helps us to understand what might happen if the channel begins to move. The FEMA fan program relies on a simple generic assumptions about alluvial fans. And the primary assumption is that flow paths are allowed to move randomly as sediment deposits and channels erode. As a result, this program should only be applied to highly active portions of alluvial fans. In reality, the flow paths may not actually be truly random, but applying this assumption facilitates making the conclusions about probability of inundation. Using a fixed relationship between depth and discharge, the fan program assumes that along any given contour, the probability of inundation over the long term is the same due to channel movement. And the contour is kind of shown there in the upper right there is the FEMA fans kind of rendition of this, and the bottom right, you can see the actual mapping of that same contour. And so the fan program simply solves for this contour length. That results in a probability of 100, 1 out of 100 for a given depth. So it's providing this contour length for us. And this procedure requires the program to use a range of flow rates. It's not just using the 1% event that's used in the HEC-RAS model. This means that the depth zone does not represent the inundated area during a 1% chance flood, but rather the area that has a probability of 1 in 100 of being inundated. So what I mean by this, for example, is that the 1 foot depth zone does not mean that the entire area could actually be covered in a foot of water, but rather it means that some part of that area could be inundated with a foot of water. Whereas on the other hand, the depth maps produced by the HEC-RAS model actually do indicate the depth of the area that would be inundated in a 1 in 100 probability event. So, and this is assuming that there's no channel movement at all in the HEC-RAS model, whereas the FEMA fan program is assuming a random channel movement. So this distinction should be kept in mind when looking at these depth zones. So let's continue to the next slide. So this slide is kind of representing how we put all this information together to come up with an inundation map. So this first block here of the geologic assessment is the first step, and that geological assessment gives us a picture of what might be capable of happening. And from that, we obtained the delineation of the active fluvial fan portions. And only the active portions were fed into the FEMA fan program. And we assumed in this case that the channels were able to move randomly and inundate pretty much any area in that active portion of the alluvial fan. So from the FEMA fan program, we get an output. We get these depths and these contour lengths, which we convert into the picture that's shown here. And then at the same time, we're running an HEC-RAS model on the same area. And the HEC-RAS model is giving us the depth that we would get if nothing moved, if the channels remained exactly as they were. And when we combine these two models, we can see there's some differences between them, and we know that the HEC-RAS model is what would initially begin to happen before any movement occurred. And so anything that happens in the HEC-RAS model that has a deeper depth or a higher velocity than what the FEMA fan program is reporting, we know that the FEMA fan program was under-predicting depth or velocity. So these get combined together into this final inundation map. And at the bottom right here, you can see an example of an inundation map. So the FEMA fan had kind of delineated these active depth zones. In this case, they're both 1 foot depth zones with different velocities. But HEC-RAS showed us that in the green and the yellow and the red coloring here, that there were areas where the velocity will in fact be higher than the FEMA fan program predicted. And the blue area shows some areas where the depth may be deeper. And in the next slide here, we'll show some more examples. Let's go ahead and look at those. So these show some final inundated maps from this project, and the legend that you see on the left is pretty typical of the maps that we've created. The fan on the right, you can see there are some areas that only have the blue coloring without the shading, and that's where the HEC-RAS model gave us information that the FEMA fan program didn't give us any information because it wasn't an active area. Whereas when you look at the map on the left, this entire area, we have information from both the HEC-RAS and the FEMA fan program. And the colored areas show us where the velocity is greater than what's depicted by the shaded area. So the yellowish area in this case is a 1 foot depth zone, and the dashed line shows the point where the velocity changes from the 7 foot to the 6 foot depth zone. But the coloring shows us areas where the velocity actually exceeds either the 7 or the 6 foot velocity. So we get that additional information by combining the two models. And the blue shading indicates where the depth would be deeper than what would be predicted from the FEMA fan program. The pink is another depth zone. In this case, it's less than a 1/2 foot depth zone, and the light blue at the top left is the 2-foot depth zone. This particular alluvial fan was one of the ones that Lisa talked about earlier on that is subject to debris or mud flows. And neither the FEMA fan program nor HEC RAS were capable of, at least not at the time this project was done, capable of analyzing debris or mud flows. And as a result, we've put this warning on these maps indicating that they are possible, and if they do occur, that things could actually be worse than what's depicted in this map. All of these maps are available, and we provided them to the Carson Watershed Subconservancy District, and that's basically what they look like. So you can go ahead and contact them if you'd like to see some of this information. Next slide. And I think Elise is going to take it from here.
All right, thanks so much, John, for sharing that information with us. So for next steps, so through this study, we really wanted to provide our partners with a better understanding of the risks associated with these 8 fans and the potential impacts to existing and future development. And then with this information, to hopefully help prioritize watershed risk and develop strategies to minimize that risk. And then lastly, taking the findings of this study and then to incorporate them into development review. And this can help inform developers and city planners on the risks associated with some of these areas. And so with that, that concludes our presentation. And I just wanted to thank our project partners again so much for their engagement and assistance throughout this study. We really do appreciate it. Our contact information is on this slide, so please feel free to reach out to John, Lou, or myself if you have any additional questions following this forum. And with that, I believe we'll be transitioning into a Q&A period shortly after our presentation. So thanks again for your attendance, and we look forward to talking to you in a little bit.